Hello everybody. In this video, you are going to learn how to convert binary numbers to octal and hexadecimal numbers directly. You are also going to see how the hexadecimal numbers are added and subtracted. This is my third lecture on the number system. In the previous videos, I have introduced how to do the conversion from one number system to another number system. There, I have shown how binary number system, octal number system, and hexadecimal number system are first converted to decimal number system and from decimal number system to other number system. But in this lecture, you are going to see direct conversion from binary number system to octal or hexadecimal without going through the intermediate step of decimal conversion before. If you haven't seen those videos, you will find the link at the end of this video. I will show the display the playlist of the entire playlist of this lecture series on computer organization and architecture. There the number system is also there. As a review, let's see that how a number is represented. A number is represented as a positional notation, n equal to a n minus 1, a n minus 2, dot dot a1, a0, then point a minus 1, a minus 2, dot dot a minus m. Just like this example, this is a decimal number 987.34 with a subscript 10 and 900 because this is in the second position. So it is 9 into 10 square. Here it is 8 into 10 to the power 1, 7 into 10 to the power 0. And after the decimal point, it is 3 into 10 to the power minus 1. And here it is 4 into 10 to the power minus 2. So this binary number 101.01, we can find out its value with the polynomial notation like this. This is the polynomial series expansion and it will evaluate to be 5.25. If we display its digit with its position and then radix r is 2 and then 2 square plus 2 to the power 1 plus 2 to the power 0 like this, it will evaluate to be 5.25. Now these are the popular number system. Binary number system has two digits 0 and 1. So a binary number is just a string of zeros and ones. Octal number, which is also called base 8, it has 8 unique digits and those range from 0 to 7. Decimal numbers from 0 to 9. And hexadecimal number has base 16 and these are from 0 to 9. Then it uses letters A, B, C, D, E, F. And A stands for 10, B stands for 11, C stands for 12. Like this, F stands for 15. Now here it is showing just a small table of decimal number 0 to 16 and its binary equivalent, octal equivalent and hexadecimal equivalent. Suppose this number, decimal number 8, in binary it is 10000. So that means decimal is more compact than binary number. And octal equivalent for 8 is 10 and hexadecimal is still 8. Similarly, 16 in decimal, in binary it is 10000 and octal 20 and hexadecimal 10. So in a computer, the binary number system is used, but because it is not a compact representation, we usually use the hexadecimal number system to represent the same binary number. So we must know how to convert between binary and hexadecimal. So a number has a integer part and a fraction part as shown here, and we know their positional notation and how to evaluate them. I am showing them here again just for a quick reference. For octal number 127.4 octal number, which evaluates to be 87.5, and this is the way to convert the octal number to decimal number and then hexadecimal number. Now we are going to see in this video how to convert the binary numbers to octal directly without going through the intermediate step of decimal number conversion. Because binary base is 2 and octal base is 8. 8 is 2 to the power 3. So any binary number, integer binary number, we are grouping 3 bits together. And this is integer, right? It is to the left hand side of the binary point. So we start grouping from the right hand side. 0 0 0 one group, then 0 1 0 second group, 1 1 1 third group, 0 1 0 fourth group, and then this there is only one more digit left, but we need 3, so we can imply it is implied that there are 2 zeros in front of it. So these 3 zeros together make one octal 0, and 0 1 0 it is only 2 in octal. 1 1 1 is octal 7, 1 0 0 is octal 4, and this is octal 1. So the answer for this big binary number is equivalent to 147208 in octal system. Similarly, here I am showing a real number with a binary point, and you also see the grouping again. Before the binary point, we start grouping from right hand side, 1 1 0, then 1 1 1, and after the binary point we start grouping from left hand side. You can see in the left hand side, from the left hand side after the binary point there is only one digit, but we will assume that there are 2 zeros after it. So 0 0 1 together it is equivalent to 4 in octal. And then this 1 1 0 is 3, 1 1 1 7, 0 0 1 is 4, 1 1 0 is 3. So the conversion of this real binary number is 3473.4 in octal. For binary to hexadecimal conversion, binary has base 2, hexadecimal base 16. 16 means 2 to the power 4. That's why the grouping will be of 4 bits together. 4 bits, it's a integer number. So 0 0 0 0, then 1 0 1 1, then 1 0 0 1, and then there is only 1 1 left. But we can assume that there are 3 zeros in front of it. If we assume that it is not changed the value of the entire number. So the hexadecimal equivalent of this 4 0 is 0, and this 1 0 1 1 is B, and 1 0 0 1 is 9, and this is 1. So this number is equivalent to 19D016, and you can see it is so much compact, so it is easy for writing and remembering the number. Now let's see an example of a real number with the integer part and the fraction part, and you can see that after the binary point there are only 2 bits, 1 1, so we have to assume there are 2 more zeros here, and if we add 2 zeros this number is equivalent to C in hexadecimal, 0 0 1 1 C for 12, and this one 1 0 1 1 it is D, 1 0 0 1 is 9, and 1 1 0 0 is 3. So this is the hexadecimal number 39D point C. Now we are going to see hexadecimal number addition. So this is the first number, which is called augend. It is 5BA9 and D058 is addend, and we have to add them. So we'll do like this. 9 plus 8 is 17, right? Then, so this is decimal 17, and then we are going to convert it into hexadecimal. So 17 in hexadecimal is 1, 1. So the least significant one will go here, and the most significant one will go here as a carry. Okay, so again, I am repeating again. 9 plus 8, we know we'll do the decimal addition because we are more used to think in terms of decimal number, and then we are going to convert it into hexadecimal. 9 plus 8 is 17, and 17 is equivalent to 1, 1 in hexadecimal. So 1 comes here and 1 goes here. Now A is 10, 10 plus 1, 11, 11 plus 5 is 16. And 16 in hexadecimal is 1, 0. Then B plus 1 is C. And 5 plus D, D is 13. And 5, 13 plus 5, 18. 18 is equivalent to 1, 2 in hexadecimal. So 2 goes there, 1 goes there, and this one comes down here. So this is the sum 1, 2, C0, 1 with subscript 16. So it is an hexadecimal number. Similarly, let's do a real hexadecimal number addition. FBA6.AB is the augend and D058.67 is the addend. So B is 11. 11 plus 7 is 18. 18 in hexadecimal is 1, 2. 2 here, 1 here. Then 10 plus 1, 11. 11 plus 6 is 17. 17 in hexadecimal is 1, 1. Then 6 plus 1, 7. 7 plus 8 is 15. 15 is equivalent to F in hexadecimal. Then 10 plus 5, 15, again F. Then B, and then this one is F plus D. 15 plus 13. So it is 28. 28 minus 16. The 28 representation in hexadecimal is 1C. So we write it like this. So this is the answer. Now subtraction, we have to be more careful. I am also given a decimal reference how we do the decimal subtraction. So we'll be following the same procedure except that it is a hexadecimal number. So you know that when we subtract, we can only subtract from a bigger number. So minuend is bigger, larger than the subtrahend, and we use the borrowing system. So 9 minus D is not possible. So we have to borrow from here. So if we borrow with respect to this column value is 16. So we are basically borrowing 16 from here. So 10 here is equivalent to 16 in hexadecimal. And as we have borrowed from here, this B becoming A. So now it is 16 plus 9, 25, 25 minus 13. So this is a C. Okay. Now A minus 0 is A. Now again we cannot do 5 minus 8. So we have to borrow from the next higher position. So we are borrowing 16 here. So 16 plus 5 is 21. 21 minus 8 is a hexadecimal D. Because we borrowed, A became 9. So 9 minus 5 is 4. So this is 4DAC. Now let's see a real number subtraction. The minuend is B483.03 and the subtrahend is 5801.67. Now because we cannot minus 3 minus 7, we have to borrow from the next higher column, but here it is a 0, so we cannot borrow from here. We will be borrowing from here. So with respect to this column is 16 times 16. Okay. So that 16 times 16 we are keeping one 16 here and another we are keeping 15 times 16 here and one 16 here, and this 3 is becoming 2. Okay, if there is any confusion you can refer to decimal subtraction, uh, like here also these are all decimal numbers. 3 minus 7 is not possible and you have to borrow, but here it is a 0, so you are from here if you borrow basically you are borrowing 100 and this 100 you are distributing here. Here you are keeping 10 and 90 you are giving it here. The 9 here is equivalent to 90 with respect to this. So 10 plus 3 13, 13 minus 7 is 6 here, and then 9 minus 6 is 3, and then you borrowed from here it became 2. So 2 minus 3 is not possible, you have to borrow from here. So this is becoming 7 and you are giving a 10 here. So 10 and 2 is 12 here now. 12 minus 3 is 9, 7 minus 2 is 5, 4 minus 1 is 3. So because we are used to decimal subtraction, I just kept that decimal number subtraction here for a quick reference, because when you borrowed from a higher location, how this 0 became 9. But here it is a hexadecimal system. I am borrowing from here, this 3 is becoming 2 and here it is F. And here this 10 is 16. So 16 plus 3 is 19, 19 minus 7 is a C. Then F is equivalent to 15. 15 minus 6 is a 9. Then 2 minus 1 is a 1. 8 minus 0 is a 8. Now 4 minus 8 is not possible. You have to borrow from here. If you borrow, B will become A. And here it is 16. This 10 is equivalent to 16. 16 plus 4 is 20. 20 minus 8 is 12. 12 is a C in hexadecimal. And here it is 10 minus 5 is a 5. So this is the way hexadecimal subtraction goes. Hope you learned it. If you need more time, please pause the video and look again.